Hello everyone, welcome back our class. So today I will introduce one a very special case, 2-qubit, the collapsed quantum circuit. That means something the 2-qubit try to entangle together, and some will create one of the case maybe collision. It's called the collapse. So but how to simulate in the simulation and how to prove. So today our lesson try to focus and okay, let's see. Okay, here is an example in the Google collapse simulation, and you can see over here we have two the quantum register and two the quantum vector x and y, x and y. And we have two classical the values, the A and B. So each part will be simulated about the different quantum state. X and Y will be 0 and this I think is 1. 2 the qubit, and the A and B simulate about the bit for classical the binary the value like 0 and 1, and over here we create about the harmonic gate, harmonic gate, and we create the circuit, and this one we can try to send tensor products, and we measure the value for each qubit. And the last one we can visualize the result on the result on the matplotlib. So here is a simulation for how this one is 2 qubits non-separable collapse quantum circuit. So you can see we have this Hadamard gate, and we have this one is positive, and we have 2 qubit state, x and y, and we have tensor products. Okay, so over here we have a result is 0 0, and we have 1 1. So and now we can test 7 case. We will test 7 case and see how the result if we use a kind of non-separable the quantum circuit. We can test which first time we can test initialize. This one is initialize the qubit 0 and 1. Initialize this. So this kind of this is 0, and this is 1. Okay, sorry. Okay, so okay, after that we can sample statistics data by the sampler, and we can calculate about the statistic and the histogram. Actually, this one to make sure after you calculate and input the data for the circuit, and you got the result, and see how result look. So this is a formula for simulation, to make a statistic. But this one is remind our one the important this kind of probability. So that means the result for after every run maybe it's different from each other. So if you see the result from the running with our result in this line is different, so that's no big problem. Okay. But have one thing, that depends, it's different or not, it depends on how you set the initial value. Okay, sorry, if you set the initial value is same to us, maybe it's the result probability maybe the same. For example, about the input, this one you input about the two value, the qubit 0 and qubit 1. So if you see over here the probability for qubit 0 1 maybe about 50%, 1.5 is 50%, 1 0 is 50% or 1.5. So if you see over here we have an initial value, so 0, this is 0, okay, this is 0, and this is 1. Yeah, this one. So after run through the quantum circuit, you can see the probability to appear this kind of value of 1, 0, 1 is about 50%. So you can see this kind of this kind of the model. And if you want to try to the first you want to negative, and this is C note. Yeah, you see the C note, the value. So after you run the tensor blocks for the Hadamard tensor blocks with identity matrix, and you have this kind of result, right? So, and yeah, after you can calculate with the identity, this identity is a matrix, you can see that's the kind of final result. And this one indicate this is 0.5. Yeah, this one is indicate. Yeah, we have you see we have a half or 1.5 or 50%. 50% that's the kind of 0, 1, and 50% is 1, 0. If you see on the screen, that is similar. Yeah, similar like this part. So you can see this part. Yeah, and okay, that is for C note. That's for first try. So we input 0 and 1, and we try to C note. Now we have go to the second part. We can second try. If you see this input, this is a qubit 0, 0, and we have a negative qubit. This one negative, right? So if you see the negative qubit, we have some different information when input in the y value. And after you see, if you input the different input from the first one, you will see. Okay, I want to say. I just say from the beginning in this lesson, if you input the different, the result may be different from our slide. Yeah, our slide. So if you see over here, different from the first one, we have 50-50, right? Now if you enter the negative, the qubit, you can see the probability for each value. Total, we have 4 possible agent state. So 1, 0, 0, 1, 0, 0, 1, 1, 0, and 1, 1. So each one when we have 25% can appear. Yeah. So this one it can calculate by this formulation. Yeah, calculate with input. Yeah, this one is input similar, right? And based on this kind by the this kind of matrix from the Hadamard gate, and we have this kind of this one is identity. Yeah, so after we calculate, so we can see we now have each part. Yeah, each part. This one is 1.25. Yeah, 1.25. This part 1.25. So we can see the 1.25 or the 25 the percentage. Yeah, 25 percentage or 1 quarter about the 1/4. So that's the probability for the collapse. Yeah, collapse. This one is explain one very important thing. If you have the 2 qubit can entangle together, if they can have create a more state, I think there is a fewer probability to collapse. But if the state, I mean, if you see over here we have a 0 and the negative, right? That's the qubit can run maybe it's the same dimension. So when we have a less collision. But is this one, we have 0 and 1, that be north and south, something like this. Maybe have the harder higher to have a problem about the collapse or collision. Yeah. So the position, I think, is the most important. The position and the direction for the qubit is very important to determine have any collision or the collapse or not. Have one thing in the third try. Yeah, we can test with positive and with qubit 1. You can see after we calculate about the tensor products, we can see this equal to the the binary or this kind of identity, the matrix, and we can see is equal to the 0, 1, and this kind of the probability is 1. Yeah, you will see this one probability is 100. Yeah, that means positive. I mean the right side, and one that mean about the south pole, right? So when this one run together, maybe it's a very high chain. Maybe this one will be create about the collapse problem. They will meet each other and create a collision. Yeah. And now we can try to the two different the positive that means the right side, negative that means the left side, right? The left side. Remember, we have a kind of direction in the the block sphere, the left hand side, and the north and the south, right? So over here we have to the value. Yeah, this input for positive, this one for negative. Negative we have one minus, yeah, minus the value. Okay. After we put this initial value and go to our Q keys, we can see well probability for collapse. Yeah, for collapse about the 50%. Yeah, and you can see this one is how to calculate in the tensor products. Yeah, and to multiply the matrix, and you can see over here we have 50, right? This one is 50% for each this kind of two value. Yeah, 50% for this, yeah, for this kind of two value for the state vector. So yes, so that is one important conclusion. The input state will be effect very significant to the output, and it depends what the state you want to input, or negative, positive, or the qubit 1 or qubit 0. The combination for different input will be generated different probability. The output is 100%, 50%, or only 25. So that depends how you combine. That is one of the other thing will be in fact in future. If you want to create a very good the quantum design, you need to think more carefully about how you input a state and how to combine. And sometimes if you have a lot of qubit, it will be create one case with entangle or the collapse is this part I just mentioned. So remember, collapse or collision, that is one of I think special case. And I hope that in future you can take when you design any quantum system, you need to look more in this special case. Okay, summary: we have two cases how we can simulate the entangle, and how we can how to combine from the input and calculate a probability for the output and see the final result. Okay, thank you everyone.